Welcome. In this video, we will be starting our series with 1.1 angles, degrees, and special triangles. So the first thing in our trigonometry course that we're going to want to think about is how do we name angles, how do we identify angles, and categorize them. So first, we'll take a look at naming angles. You'll see on the right, we have an angle called theta. This is just a Greek letter that we'll use primarily to name the measure of an angle. The angle is made up of two rays. One ray is called the initial side, and the second ray is called the terminal side. So where the angle starts and stops. When we consider the name of this angle, we can name it either angle O or angle BOA. So these are two names of that same angle, angle BOA or angle O. When we think about angles, they could either have a positive or a negative result. When I consider a positive angle, I could consider the set of an x-axis setup. And a positive angle is going to be going from the initial side and then it is going to be going in the counterclockwise direction. So we are going to be traveling counterclockwise for any positive angle, or we can consider going in the clockwise direction for any negative angle, again with the initial side and then the terminal side. So we can highlight those there. There are some specific types of angles that we'll also want to be referring to. The right angle is the angle of 90 degrees. We see that in our first picture on the left. The straight angle is 180 degrees. It looks like a straight line with a pivot point in the middle or a vertex. And we have acute angles. They are always between 0 and 90 degrees. And then an obtuse angle is any angle from 90 to 180. It would be obtuse. So we have those specific angles that we want to keep in mind. Kind of a review from geometry. So the first topic with angles that we're going to want to be concerned with is the idea of complementary and supplementary angles. So two angles that add to 90 degrees are called complementary angles, and two angles that add up to 180 degrees are called supplementary angles. So let's take a look at a couple examples of finding the complement and the supplement of each of these angles. So if we start with a 47-degree angle and want to find its complement and supplement, let's start with the complement. We'll just say that's C. The complement of a 47-degree angle, we would say would be 90 degrees minus 47 degrees. And that would end up being a 43-degree angle. That would be the complement of a 47-degree angle. We can consider the supplement of that same angle. We'll call that S. We would like to add up to 180. In other words, 180 subtract our angle would give us our supplement. That would end up being 133. If If I consider a 115-degree angle and first want to find its complement, again, to find a complement, I need to have two angles add to 90 degrees. So what I could do is take my 90, subtract my given angle. If I subtract my given angle, this would say that the complement of this angle is going to be negative 25 degrees. So that would mean that negative 25 and 115 would add up to 90 degrees. Those would be complements of one another. And then we can finally finish up with the supplement. The supplement of 115, if I want to add to 180, subtract my given angle, and that would give me 65. If I wanted to think about this principle more generally, with just any given value theta, if I want the complement of a arbitrary angle theta, I could say that that would be just 90 degrees minus theta. And just leave it like that. And my supplement could just be 180 degrees minus my given angle theta. Whatever theta is equal to, I know its complement and supplement can be found by 90 minus theta or 180 minus theta, respectively. So that is complementary and supplementary angles. The next item we're going to take a look at are some special triangles, and we'll first take a look at the idea of the Pythagorean theorem through one example. So for this example, we have a hypotenuse of a right triangle measures x plus 1 units, and the length of the triangle, or the and the legs of the triangle measure x and 5 units. So I have a hypotenuse of x plus 1 and legs of x and 5. And we'd like to go out and find the value of x. So many times in trigonometry, it's important to draw a picture, and this is a great opportunity to draw our first picture of our triangle. Our hypotenuse is known to be x plus 1, and our legs are 5 and x. And it doesn't matter which leg we choose here. We could use either one. We could set up our equation for the Pythagorean theorem. That would say that my hypotenuse squared is equal to the legs squared and added together. So a squared plus b squared equals c squared again. Again, this is a right triangle. So we know we have a 90-degree angle across from our hypotenuse. So it looks like we're going to have to do a little bit of algebra here to FOIL out our x plus 1, and then we'll see if we can have some like terms to combine. So if I square x plus 1 out, we can say that that's the first term squared, x squared, plus 2 times the product. That would be 2 times x times 1. That's 2x. And then 1 squared is going to give me 1 is equal to x squared plus 5 squared is 25. We can continue to simplify here and add like terms. If I consider just subtracting the x squared, and we can subtract 25 from both sides. We can cancel the right side out to 0, and we'll have remaining 2x minus 24. And we can continue this process, just add over our 24. We would get 2x is equal to 24, or x is equal to positive 12 when we divide. So I found the value for x. If I want to consider all sides of the triangle, I could say that one leg here is going to be length 12, and the hypotenuse here, x plus 1, is going to be length 13. This brings up a subject of Pythagorean triples. These are three whole numbers that give me a perfect right triangle. So two legs and a hypotenuse that are all whole numbers that give me a full right triangle. I have a list over here on the right of these perfect Pythagorean triples, which are, again, three whole numbers that create a right triangle. So the most common ones you'll see are the 3, 4, 5 triangle. We'll see that quite a bit in trigonometry. The 5, 12, 13 triangle, that's the one we just solved for in our example. And you can see a list of quite a few more. This list goes on and on. It's kind of a cool list in terms of the mathematics behind it, but it might be good to get familiar with at least the first few on this list, because we will see them quite a few times. So the Pythagorean theorem is going to have an integral part of our course, so let's remember this as we go into the rest of our course. The next topic we can take a look at is the special right triangles. The first one is the 30, 60, 90 triangle. The 30, 60, 90 triangle is important to us, especially when we get into what we'll call our unit circle, and when we go to work with the sine, the cosine, and the tangent function. So a 30, 60, 90 triangle has a specific ratio pattern for its sides. Across from the short leg here, we'll have unit length t. The hypotenuse will be 2 times the length of our short side, and the long side will be square root 3 times the short side. So this ratio of sides will hold true for all 30, 60, 90 triangles. So let's get used to kind of working with this ratio. In this example, we have the short side of a 30, 60, 90 triangle is 5 inches. Find the other two sides of the triangle. Okay, so let's draw another picture of this 30, 60, 90 triangle and solve for our remaining sides. So I have my 30, 60, 90 triangle. And I'm given that the short side of the triangle is 5 inches. Let's label that triangle once again. 30, 60, 90 is back. And our short side here is going to be 5 inches. So let's consider what this is. If this is length and we call this length t, we know the hypotenuse is going to be 2 times that length t, and my long side is going to be t roots of 3. So we'll keep that ratio for any 60, 90 triangle, and this is no different. So we can say that if t is equal to 5, that short side, our long side is 2 times t, which would give us 10 inches. And our long side here will be t square roots of 3 or 5 square roots of 3 for that long side. So we've solved for each of our sides, and again, each of these are in inches, we can label. 10 for the hypotenuse and 5 root 3 for the long side. Let's take a look at another one of these 30, 60, 90 triangles examples. This type gives us the long side of the 30, 60, 90 triangle is 4 feet. We want to go out and solve for the other sides. So again, let's label a triangle. "30, 60, and my 90. And this gives me the long side. So this is 4 feet. And again, remember that this ratio here, if I just put out my ratios, this is length t, this is 2t, and this would be t roots of 3. So we want to consider a ratio where I know the t roots of 3 side, and I like to go out first to solve for t. So I can set up a ratio here to solve this triangle. I know that 4 feet is to t roots of 3. That ratio is equal to t over, well, I want to consider maybe this as just an x. I want to solve for that length there. So if I do some cross multiplication here, I can see that 4t is equal to x times t roots of 3. And if I divide both sides to solve for x here by t roots of 3, I can see that these will cancel. My t's will cancel here, and the x length here is just going to be equal to 4 over the root of 3. If I want to think about rationalizing that denominator, we can multiply by the root of 3 over the root of 3. We'll do this quite often. And this final result we can say is 4 root 3 over 3. So that would be my short side there. 4 roots of 3 over 3. And if I consider doubling that side to grab my hypotenuse, 2 times t here, that length side, if I double that, that will end up being 8 roots of 3 over 3. And again, both of these are in feet. So this is a look at, again, a 30, 60, 90 triangle, working out those side lengths. The last special triangle that we'll look at is a 45, 45, 90. In terms of 45, 45, 90, we'll notice that the unit lengths on the legs, t, and then the hypotenuse will be t roots of 2. So this ratio will hold for all 45, 45, 90 triangles. So we'll take a look at considering a ratio here with our 45, 45, 90. In this example, we have the hypotenuse of a 45, 45, 90 triangle is 7 meters. We want to find the other 2 sides of the triangle. In other words, we'd like to know the legs. So if I have a 45, 45, 90, so these are equal 45s. We know the ratio here is t roots of 2, and this would just be length 2. If I know that this length here is just 7, I can consider just solving for my t. So 7 is equal to t roots of 2. So I can divide by the root of 2. 7 over the root of 2 is equal to t. Or if I consider rationalizing that denominator again, I can multiply by the root of 2 over the root of 2 to rationalize it. And so this will give us that t is going to be equal to 7 root 2 over square root of 2 squared will just give us 2. And again, we know that this is the same side for both of our side lengths, since this is a 45, 45, 90. We'll finish this video with an application question with a flagpole using our special right triangle techniques. So this question says, if angle B is 60 degrees and length AB is 25 feet in our picture, find the distance from A to D, to the top of the flagpole. Round to the nearest foot. So we would like to go out and solve for this red line, and I'll just label this as an X for right now, this length A to D. So let's first consider a few things on our triangle. We know that angle B here, down below on the ground, is a 60-degree angle. So let's consider first looking at our triangle. If I redraw my triangle that's on the ground, this is A, this is B, and this is C. This is again the triangle that is flat on our ground. We know this is a 60-degree. This would make it a 30, and that's a 90. And we know the length from AB is 25 feet. So one thing that might be important for us to know is, what is the length from A to C? We could call that Y. Because that's going to relate the triangle on the ground to the vertical triangle that we have against the flagpole. So let's consider again the ratios of our right triangle. I know if this is the short side, this would be the length of t. So this would give me the length of t equal to 25. The hypotenuse is 2 times t, and the long side is t roots of 3. So when I consider the length of y here, that's just going to be my length of t, the unit side, times the root of 3. So y here, on my 30, 60, 90 triangle, I can say is going to be 25 roots of 3. So this helps me relate the triangle that is in the vertical direction. So notice here, y, we can represent here as 25 roots of 3. I'll just label that right there. So now consider our vertical triangle. We'll do this in a different color, just to distinguish. The vertical triangle that we have set up is still a right triangle, and therefore, if I know the two legs of that triangle, I can use the Pythagorean theorem to solve for the hypotenuse. So the second stage of our problem, we can use the Pythagorean theorem, and we can say that a squared, 75, plus b squared, that's 25 roots of 3, quantity squared, is equal to our x squared. Now we just have to multiply here to find our results. So 75 times 75, you'll get 5,625. If you multiply 25 times 25, that's 625, and then we also need to square the root 3. So all together there, when we square the second value, we'll get 1,875 equal to x squared. We can add these two numbers together to get 7,500 is equal to x squared. And then finally take a square root to solve for x. And if you take a square root and round to the nearest whole number, you'll get 86 feet for the length of that hypotenuse. So the length from A to D here is going to be 86 feet. So thank you for watching. I'll see you in the next video.